Hi everyone. Um, this is Devansh, and today I'll be presenting the my final project. It's titled Sudoku Solver: A Computer Vision Approach, and I am the sole member of Group 11. So let's get started. First, let's take a look at the project overview. So the general idea is what I'm going to go through with this. So in the beginning, my initial aim was to make an automated system that can essentially solve a Sudoku puzzle. And I think the most interesting part of this kind of a project was to create a live project where I can actually show this to you, where I would use camera footage, which is being fed live to the software pipeline, and then solve and display the solution right there and then. And so the general idea of this project was to essentially we want to be able to collect the data, the image data. We want to be able to process it. Then we the most important step, we want to understand what is there in the image, and then look for the relevant area, and then solve the puzzle essentially. So let us now take a look at what the evolution of the project looked like. So there isn't, I wouldn't say is too much of a difference, at least coding wise, where the initial approach and updated approach are different. But there are definitely some differences, and I'll just go over that right now. So initially, like I mentioned, intended to use the webcam feed, or like a continuity device, such as my mobile phone, the camera of that device to get in live feed. We wanted to then apply pre-processing, some pre-processing techniques that I'll go over later. You want to find the contours, essentially the lines, and then use these significant lines to find the main grid of the puzzle. Once we find the grid, we want to then break it into 81 even boxes, and then process each box to then eventually get a prediction on the box. Once we have the predictions, we want to be able to recreate the puzzle, using like in code. So essentially, like some sort of a 2D array, essentially. And then this 2D array, we want to pass it to the Sudoku solver, and then that would solve the puzzle. And then we want to be able to overlay the solution. And then the updated approach, which I changed a little bit, um, this was essentially because um, there isn't a real issue with live footage, but the issue persists in the later aspect of the project, which is why I decided to move from the live footage to static image, because it was easier to debug and test. But if I can get the pipeline to run, so as you can see, the updated approach is fairly similar. Difference being, we use a static image, we follow the rest of all the same steps, but then instead of actually solving, we want to focus on looking at the prediction accuracy. And this is because that's what I was talking about, that I face some issues with the prediction um, on a well-trained model, that too, but I face some prediction issues. And so if we cannot get a relevant prediction, or and a very accurate prediction, not relevant, we can't really solve the puzzle, because that's probably just going to give us an answer back saying it's unsolvable, or it's a incorrect puzzle. And one more thing I want to mention is that I the the aim of this project is not to focus on the solving part of the Sudoku, because those are already well implemented algorithms out there. So I just used a file that was already working, and I checked that it uses backtracking to solve the Sudoku puzzle, which I believe is already pretty good. So there is no aim to work on that, but my aim was to create a pipeline where I can, read in um, an image or a live feed, find the puzzle, accurately rebuild the puzzle virtually in code, and then pass that to the solver, and then again, once again, overlay the solution back onto that. A little bit ambitious, but like I said, I'm not interested in the Sudoku solving part, because that's more like a data structures or algorithms course project. So let's have a look at the relevant works. So the I found works that were not only research but also some casual work, and essentially I would like to believe that my inspiration comes from the casual works, but irrelevant of that, I'll go over both. So some relevant works include Nugent and the rest of the authors that learn to solve Sudoku with a computer vision aided approach, and these authors employed the use of a KNN model that they converted to find or essentially rebuild um, the image data, and then rebuild that image data into a puzzle. The second research work essentially employed a bunch of computational logic to find um, the contours, and specifically they wanted to also use some libraries which were more mathematically intensive. Looking at their results, I noticed that they did also focus on looking at static images in the beginning. And I believe that is a general approach in such a project, because you want to be able to first solve a static image before moving on to a live feed. And for the casual works, essentially they have done a bunch of different methods, but a lot of overlap between the functions that they're using, such as Gaussian blur, thresholding, warping, um, and so I've taken a bunch of inspiration from them too. So it's essentially a combined inspirational journey when it comes to finding what to find, plug and chug. Now about the software design. So here is a here is an image that contains all of the steps that I've already explained. Firstly, you have the input image. We then apply, we firstly invert the image, essentially not invert the image, we do a grayscale, we turn it into grayscale. We then apply Gaussian blur, and then we do thresholding to get that second image over here. We then use we then use some we try to find the contours, and then using those contours we also want to get we need to it's essential to find the right contour. So to say that this one is the top left of the grid, for example, that is was a little bit complicated, but um using a bunch of NumPy libraries, I believe it is easier to solve. And then we get this grid. So we then basically divide this grid into 81 even um, boxes, and then pass each box to the CNN model. Um, and so I would like to mention that this CNN model was another aspect of this project where I wanted to get my hands dirty with PyTorch library and made a MNIST trained MNIST dataset trained model in PyTorch that I initially believed would be good enough, but we'll see later that it is not perfect. And then yes, so we pass these boxes into this model. It we get the prediction, we rebuild the puzzle, and then we pass that to the Sudoku solver, and the puzzle is then solved. And then if we want to overlay it, we can do that, or if you want to provide the solution as just display it in console or write a CSV file, we can do any of those things. So coming back, so I mentioned I trained the model myself. So I wanted to get my hands dirty with PyTorch. So I decided why not, use this opportunity to do a little bit of PyTorch coding. So I created this MNIST PyTorch model. Obviously, this is a very common data set. So you can find code for this almost anywhere, but um, the general breakdown of the model is that it has two convolution layers, a one dropout layer, and two fully connected layers. And the way PyTorch coding works is first you create a class for the model, and then you then define each of the layers, and then you use the forward. You have to also define a forward function which essentially does the work, which is where the work happens, is essentially you apply the activation functions for each of the outputs for each of the layers, and then you build it from that. So obviously in this image you can't see it, but essentially here in PyTorch, these activation related functions, the max pools and the ReLUs, are done in a different function, while these convolution layers and these fully connected layers um, are again separate. They're in the init function, while those activation functions are written in the forward function. So it was fun learning this, and I love that. Um, Coming back to the description of the source code. So we have a bunch of these files that you can find in the in the repository. So firstly, we have the accuracy.py. So this is for the later stages when I was able to complete the pipeline. And then we wanted to check the accuracy of the predictions. So this had to be done a little bit manually. Essentially, not the coding part, but essentially the implementation of this. So to get the numbers, I had to like manually do that. Then the CNN visual is essentially just a file that I created a visualization for the model, the MNIST dataset trained model. The main.py is for the main functions. The mnist.pytorch is showing how I have trained it. This is the mnist dot underscore state underscore 97.pth. This is the actual model parameters, or the model saved in a file. Model.onnx onyx is just the file I generated from CNN underscore visual, which I use to create the visualization. And then we have the README file, we have the Sudoku solver, which is just whose job is just to solve the Sudoku. And as I said, I don't get into that. We have the test images, which is a folder and it has 3 images, and we have the utils.py, which contains all the helper functions. Right. So now I'm going to do a quick demo to show you each of the stages of each of the stages of the code, and then how how it works, how I have those outputs. So let's just get into that. So here I have my code already. Here's the main file. We have the utils over here, and so when in the beginning, as you can see, we are reading in the image, and if we don't find the image, we just say that we're reading in the model. The model loaded, we want to show that as well. But then firstly, as I mentioned, we want to so let's go back here. So we want to first do a thresholding, which was not just thresholding, it was a combination of those. It was turning the image into grayscale, um, then applying Gaussian blur, and then doing thresholding. So let's run this. And then let's see what we get once we do the thresholding. There you go. There you can see that this is what the pre-processed image looks like. I'm going to hit Q, which is what I have, and then now I'm going to run the next part of this. So next step is to get contours and select grid. So here we are doing that. Essentially, we are getting two things back from the find grid function. So the find grid function is right here. Essentially, we're doing some math to find the largest set of contours on the that are connected, and so we get those contours back in best CNT, and then we also get the cropped grid. So now let's take a look at the cropped grid. Let me save this and rerun this. As you can see, right here, this is what the cropped grid would look like, and you can hit Q, move on. Let me remove this. Now this function right here, this was what I was using for live video feed when I was initially working on this, because when we have a live video feed, we don't have a perfect straight angle to our image most of the time. Well, not most of the time, we can adjust it, but using warping, we can essentially even if the camera is looking at the image in um, a slighted or tilted angle, we can still get the image in a straight or from a straight point of view, from a front facing point of view. But since I'm not doing a live feed, I'm going to skip this. We're going to go into the next stage, which is to split the boxes. As I said, we find the grid, now we split the boxes. So this is function we use for splitting boxes. And then I'm going to show what one of these boxes looks like. So right now I'm using the same image. Sorry about that. I'm using the same image. So I'm gonna show you the third box, or boxes index 2. So which would be 5. So let's take a look at that. What does that one box look like? And as you can see over here, that's a 5. We can confirm that 235, so that's a 5. So the boxes are being made, and then that's what one box looks like. Hit Q, we're going to move on. Now we want to step 4 was to prep the boxes for the model. So obviously the MNIST model is trained on a 28 by 28, and it has some specifications of how it takes how the inputs are made for the trained model. So we want to prep the boxes, each box, and then get an array of all those boxes back, of those pet boxes, and then um we want to throw our model and these prepped boxes to get our predictions. And then we want to, since we right now, since obviously the prediction isn't perfect, like I mentioned, I just want to display the image or the prediction um on the console, and just show you what it looks like, what the numbers look like. So I'm just gonna run this, and I'm gonna stop it because we only want to look at the console output. I put a dashed line here to reflect when does one start and end. As you can see, this is a 1D area of length 81, essentially showing the prediction for each box. So like you can see 235, it's saying the first three boxes are 235. And so if you look at the test image, so it's 235, and then we have um, three zeros, and then we have 070. Yeah, so as you can see, so 235, three zeros, 070. Essentially here I've decided to go with 0 and not none, as to reflect a blank, because obviously we cannot have a 0 in our uh, in a Sudoku puzzle. So I've decided to go with a 0 that way, to reflect a blank. And so it seems to do well, but it's what I want to show is it's not perfect. Right. So now what I did was I had to manually get this, because I had to also define my own accuracy prediction metrics. So here is what the evaluation metrics and the results look like. So I have three metrics. So we have digit accuracy, we have blank box accuracy, and overall accuracy. So digit accuracy is essentially just the percentage of correctly identified digits out of the non-blank boxes. So any box that actually has a digit in it, are we accurately classifying that as a digit? And then we have the same for blank box. So if it's a blank box, are we able to through code at least say that, oh, is this is a zero, this is a blank? We want to make sure that this is what we're going to be um, basically solving for. And then we have the overall accuracy, essentially just adding those two up. And so we have now three images, which is what I went through. And as you can see, blank box accuracy is essentially it is doing well. So the image, or sorry, the model is able to predict that a box is blank. One of the ways I actually did that was to say that a box is blank if the model can't the highest um, the confidence of the uh, best prediction that it's giving. So for example, let's say that this box, for example, this is it's predicted zero. So let's say the model was predicting this to be let's say 8, but the confidence of that prediction was let's say like 35-45%. So what I did was I basically made a condition that, okay, if you cannot predict a box properly very well, so like at least 85 to 90% confidence interval or more, um then it's probably a blank and you're just hallucinating, or you're probably just trying to give me an answer because the MNIST dataset isn't trained for blank boxes, right? So it's trying to give me some sort of an answer. So but we don't want that, we want a blank. So what I did is I just applied some sort of a thresholding in the get digits function here, saying that, okay, so I chose 80%. So I'm saying, okay, the confidence if the confidence is not at least 80%, I'm not going to use your prediction. I'm just going to say it's probably a blank. That's what I'm doing there. And so, the blank box accuracy is fairly good. And then the digit accuracy is where we are losing out. And especially image one is doing slightly under 60%. So here's the issue in this whole situation. So if you're going to solve a Sudoku puzzle, we need to get every box correctly identified. One, it being a blank or not a blank, and if it's not a blank, what digit it is, and it has to be the correct digit. Because if we pass in a different when we rebuild this Sudoku puzzle, if we pass in something that's not the same thing that's actually that's not on the actual image, then we obviously will get a different answer, and then that answer is not the correct answer. So we need to get the correct um, solution. So I want to get on to the conclusion. So essentially, in this project, I have made a pipeline that wants to solve the Sudoku puzzles, that can solve the Sudoku puzzles. Obviously, it's not doing it perfectly. I was also able to build an MNIST model from scratch. Now, obviously, this is not a big deal, but gave me an opportunity to get my hands dirty with some PyTorch code because I believe PyTorch is a better library. And then I was able to I ran some predictions. Prediction accuracy is decent, but it's not perfect. And then so obviously I mentioned we need to have a near perfect identification of the grid to continue. And then I intend to continue doing this project because I think I'm right there at the end, but it's not perfect. So if I can maybe do a better pre-processing of the image, or maybe fine-tune the MNIST model to work better on this, then maybe I can get a near perfect prediction, which I can then use to actually solve the problem. I know people have been able to solve it, so it's definitely doable. Coming to the lessons I learned, this definitely reignited a passion for me for coding into PyTorch and computer vision. Just fairly ambitious in the beginning. To be honest, I thought it would not be as difficult, but definitely it is more complex. I came to the realization when I actually started getting the predictions that, oh, it's the predictions aren't perfect, so I would actually have to spend more time trying to get those right, because the the solving part is obviously being taken care of. So once again, I overestimated MNIST model's accuracy. I thought that, if the MNIST model is already does pretty well, the images are fairly similar to those. Obviously, they're not handwritten, but they're close. And obviously, I don't have a personalized data set to run my own model on, or so train my model on those specific ones. These images are random, so not fair for me to um, overestimate MNIST model's accuracy, but I unfortunately did that. But yeah, I was surprised by how well or optimized the OpenCV functions are, and then how quickly you can actually process and show even live feeds first, because I was working with live feeds in the beginning. And for future work, as I mentioned, I would love to continue working on this, and maybe, complete this, be able to do the whole project that I had initially started with. And future work is to be able to perfectly find the grid. And if we can do that, the rest I think is a cakewalk. Maybe change it to the live feed, and then if we change it to the live feed, we might have to apply warping. But I still think, because I was doing it before, I think the live feed is not the issue. The issue is prediction. So if we can get the prediction to be better, or well, near perfect, we can actually solve this project. And yeah, I think that's it for my presentation. Thank you for watching. Hope you have a good day.